final technical session of SBMF. I think there will be a further keynote later today, and then just the closing. So I assume that the organizers have saved the best talks for last on a Friday afternoon, at least here in Europe. The first presentation will be by Mohammed Rizwan Ali, who is actually from HVL, our institution. Please, Rizwan, go ahead. You have like 20 minutes, and then we have time for questions.
Thank you, Volker, for nice introduction. Thank you, everyone, for here. Myself, Mohammed Rizwan Ali. Today, I am going to present the preliminary work of my PhD project with title Cost Analysis for an Actor-Based Workflow Modeling Language. I will start my presentation by defining some terms like workflow is a sequence of tasks that are carried out by user-defined rules or some conditions. Workflow planning is to define some workflows and execute them considering some factors like budget of a project, deadline, and available resources. In every organization, our domain expert is a person who helps a planner to plan and execute a workflow properly. He helps a planner to take some strategic decisions in some situations, like when there is a resource is missing or when a workflow is not going to meet a decided deadline. So domain expert takes strategic decisions and ensures that optimal resources are deployed. In general, right now, every organization is trying or working beyond its boundaries to achieve and collaborating with other workflows to achieve some common goals. For example, a workflow to diagnose a patient may have collaboration of 3 different workflows. For example, first one is a workflow of a clinic where a doctor takes a sample of a patient, and second one then can collaborate with him is the workflow of a pathology lab where the samples are being tested. And the third workflow that can collaborate with these 2 workflows can be workflow of a courier company who is responsible to take samples from a clinic to laboratory. However, in cross-organizational workflows, as every workflow have his own domain expert who ensures about the proper execution of that workflow and who have deep understanding and knowledge about that domain. But in general, in collaborative workflows, maybe our domain expert may don't have a common understanding of all workflows who are collaborating and sharing some resources with each other. For example, if we have we have collaboration of 3 workflows who share some resources with each other. For example, a domain expert or planner for workflow 2 takes some changes in workflow 2, for example, in task 1. Then though this change is for betterment of workflow 2, but as workflow 2 is connected and sharing some resources with workflow 1 and workflow 3, so this change can propagate some negative impacts on other collaborating workflows. Furthermore, in literature, extensive research has been done in the area of workflow planning. For example, BPEL and BPMN have been developed to specify some business processes. Furthermore, BPEL and BPMN both have been formalized with the help of color petri nets. And in addition, some pi calculus and time automata, they have been used to analyze and reason about models in business processes. Furthermore, ABS, which is Abstract Behavioral Specification Modeling Language, is a modeling language that is extensively used in the area of cloud computing and distributed systems. In ABS, it have some support for resources with the name deployment component. However, in ABS, the deployment component have limited support for resources. It have only resources may be a type of CPU usage or memory bandwidth, etc. So in general, all the available tools and techniques they might have, according to our knowledge, they might have some limited support for the resources and strategic decision making for the close organizational workflows that are sharing some resources. So our research objective is to define formally some cross-organizational workflows and allow planner to simulate and allocate resources to workflows, and also allow planner to estimate the effect of changes in one workflow to other collaborating workflows before the implementation of the changes. Therefore, our proposed approach is just to define a formal modeling language. Then after the language, we will have a cross-organizational workflow modeled in proposed language. Then we have proposed a static cost analysis, who is with the help of this analysis, we are just translating our model into cost equation set. And then with the help of some of the shelf solver, we are over approximating the execution time of collaborating workflows. First, I will discuss about the language. It's a resource planning language, RPL. The language have formal syntax and semantics. It have explicit notions for task dependencies, resource allocations, and time advancement. The language also captures the interaction between cross-organizational workflows. Also, the language have actor-based concurrency model. It uses cooperative scheduling, and all asynchronously running methods are synchronized with the help of a future, which is like a mailbox. This is the syntax of our language. Here, a program may have a resource map, possibly empty declaration of classes, and a body of main method, where in a main method we have some attributes and sequence of statements. Class declaration have a keyword class followed by a class name and a body of a class, where a body of class have class attributes and declaration of class methods. Methods have a signature followed by a method body, where a signature have a return type and followed by a name of method and possibly empty list of formal parameters. In RPL, the types may have some basic type that are integer or maybe Boolean or unit. It can have classes and a special type, which is a future, as I explained earlier, that language supports actor-based concurrency model. So all actors can directly send or receive messages to each other. And these messages are tightly coupled with a mailbox called future. So here future is that type who is associated with each asynchronous method invocation. Expressions may have some variable X, guard G, or this special identifier for currently executing object. Guard may be a Boolean expression. It can have a return test that is useful for checking either a future has been resolved or not, and it can be a conjunction of some guards. In statements, we have assignment statement that have a right-hand side, and the right-hand side might have some statements like it can be an expression, it can be a creation of new object, it can be a get statement who is used to get a value from a future. It can be a synchronous method invocation where X is a name of object on which this method is going to be run, and followed by a list of formal parameters. Here in synchronous method invocation, we have specific term after, which is followed by a list of possibly empty future test runs. This means that all these futures have been resolved before the activation of this method. This means that these futures should be resolved. This means that all the methods who are asynchronously executing and are associated with these type of futures have been synchronized and have returned some value. Similarly, we have a statement for asynchronous method invocation. We have a special statement to acquire some resources, where this statement hold is acquiring E number of R resources. Similarly, we are releasing E number of R resources. In our language, we have a unique statement, cost of E, which is consuming E units of time. We have a wait statement that is just waiting for a future to be resolved. Remaining statements are standard. Furthermore, we have defined runtime syntax of language, which is a configuration that can be an empty configuration. It might be a resource, which is a mapping from a resource type R to some value V. It can be an object, which is a tuple containing O object identifier. A is a object field, which is a mapping from some variable to values. P is a active process, which can be idle, or it can be a binding of a local variable with some statement. And Q is a pool of suspended tasks. We have a future, which is a pair of a future identifier F and a value. A value can be a value or a bottom. Here, bottom specifies that this future has not been resolved yet. Configuration can be an invocation of method M on object O with future F and formal variables V. This is just to show the operational semantic of our language. I am sorry, I have put a lot in one slide, so I'm not going to explain all of them. I will just explain the relevant one. We have a synchronous call where, first of all, we check either all the futures after have been resolved or not. So first of all, we will check if all the futures have some value and neither have bottom. So we can proceed further, and we will create a new fresh future, and we have an object which is evaluated by first parameter. Then we will have a method invocation on new object with new future with formal parameters and method name, and the new future is assigned a bottom. Furthermore, the statement hold is acquiring some number of resources. Here we have a restriction. If all required resources are available, then we can proceed. Otherwise, we have to wait until all the required resources are available. In statement release, we are just releasing resources and assigning them to resource map. Here, this is a special rule which updates a configuration with some time. Whenever there is the condition, this premises is strong stable. I'm not going into much technical detail here. So simply, this is a condition when our configuration is stuck and it cannot proceed further without consuming some time. So at this rule will consume a minimum time to make configuration executable. So here this is we have 5 different cases that are used to make a configuration executable from a stuck state. For the analysis, first of all, we model a program. We model cross-organizational workflows in our proposed language. After, we apply analysis in a sense that first of all, we identify a set of potential interfering objects. After identifying these objects, we apply a method translate to each body of every method. We iterate this approach for each method. At the end, when we have applied this approach to every method, including main method of a program, we will have a constraint set. Then we can feed the constraints and set to some off-the-shelf constraint solver, and then we can have over approximation of workflow execution time. So this is the code of translate method, that is translating a program into cost equation set. It have 8 different cases. I'm not going to explain all of them due to shortage of some time. We have an example here that have 3 different methods, and the fourth one is the main method. So we apply our analysis to this model. Here we apply our analysis to method M1, and after applying method, we will have a cost in form of CM3, which is the execution time of method 3. This means that method cost of method 1 is depending on the cost of execution time of method 3. Similarly, after applying this approach on method 2, this cost depends on the execution time of method 3 plus execution time of method 1. And execution time of method 3 is K here, which is some constant value. After applying our approach on main method, we have a cost equation in the form of this, which might need CM2 and CM3, which I explained earlier is the execution time of method 2, execution time of method 3. So there in this way we can have some cost equation set that can be used to over approximate the execution of our collaborating workflows. To conclude my talk, as a summary, in this research, we have defined a resource-aware formal modeling language. Also, we have proposed a static cost analysis that is over approximating the execution time of the program. For a future plan, we are enriching our language. Right now, our language have a limited support. For example, here in our language, for resources, we only have a number of resources. So we are enriching our language in a sense that some resource features like experience of a person or speed of a machine can be explicitly specified. And this can be useful in decision making, that if some resource is missing, then we can decide who is missing, and then who should be take control of, who should work instead of this resource. So this all kind of decision makings will be based on some resource features. Also, we are trying to extend our analysis. Right now, our analysis has assumption that all asynchronous method invocations have been synchronized and all programs terminate. So we are thinking, we will think about non-terminating programs in future. Also, for the verification purpose, we are aiming to use key ABS, which is a verifier for ABS language. So we aim to extend key ABS in a sense that it can be helpful for the verification of our proposed language, RPL. Furthermore, as a next step, we aim to evaluate our approach with the help of some case study. For that, we are working with hospital pathology department, and we aim to use their workflow as an evaluation of our approach. So this was from my side. Thank you very much for your attention. If you have any questions, please continue. Thank you.
Thank you very much, Rizwan.
Thank you.
We have time for questions from the audience. I'll give everyone a little bit time.
I have a question.
Okay, Sergio, go ahead, please.
Yeah, this is very interesting. I would like to know a bit more about the examples that you're trying to model for future work. What kind of workflows are those?
Sorry, examples of
Yeah, you said that for future work, you want to apply this to some, companies' workflows, right?
yeah.
I was wondering if you already know what they do and what they do.
Yeah, actually, we are working with the pathology department of hospital in Bergen. So they are in a process to digitalize their workflow. So we are collaborating with them, and my task is to just for the resource optimization. I will help them to for resource optimization, because right now they are facing a lot of problem, because if some resource is missing, because they have some sequence of stages from registration to pathologist. So if someone is missing, they are unable to identify who will work instead of that one. So they are just trying to automate their system for decision making, for resource optimization, and they want to get to know who is working and what is doing and who is missing. Are we going to meet deadline or not? So my task will be just to help them in resource allocation and resource scheduling. We also have some postdocs and other PhDs who are working on other domains for that.
Okay, thank you. That's very interesting. Thank you.
There's a question from Lucas in the Q&A. Does Lucas have a chance to ask it directly?
I don't think so.
Okay, so his question is, do you plan to integrate your language with existing workflow languages like BPMN, BPEL, or activity diagrams?
Actually, for my PhD duration, I am not sure I can be able to do this, but in a long goal, we are aiming to make it some user friendly. So a user can directly dragging or dropping some user interface can make it helpful.
Okay.
Yeah.
Lucas, just follow up if you still have another question, or if that was not clear. Do we have anyone else? Because even though I see Rizwan regularly, I also have a question. If you could go in your slides a little bit back to the beginning where you had the tasks that somehow synchronize in a diagram. It's one of your introductory graphics. Oops, many overlays, sorry for that. Yeah, this one. Okay, so these are, I mean, this is an abstract description, I guess, right? So there are three workflows that are somehow running in parallel, and then they synchronize. So I guess the workflows need to be modeled, of course, in your framework. And do you need a single root for the different tasks?
For this, yeah, for that case, we will have a knowledge base that will be shared again across all workflows. So we will be able to identify and know what is going on in each workflow. So it will be interaction point between all the workflows.
Yeah, no, I was just thinking, so how later in your modeling program, how you set this up, if I need to first, I guess I need to make aware each pair of workflows that they can somehow talk to each other. But yeah. I thought like your language was a little bit restricted, so probably I need like one root, or I'm suspecting I need one root that sets up the different branches of your workflows somehow.
Yeah.
But okay, we can discuss this maybe not next week, but after Christmas. Marius has a question. Please go ahead.
Yes, so can you comment a bit about your cost analysis? What is the major challenge? So obviously you add costs which are sequential and you take the maximum of costs that are parallel. Are there any operations that bring about particular challenges?
Here, actually, because we have two different notions of synchronization. So we have synchronous method invocation and asynchronous method invocation. So we try to identify all those objects that can interfere each other. So here we just try to over approximate the execution time. So as you told that here the analysis have just limited in future. We are thinking to extend our analysis in the sense that it can be associated with resources. If we change this resource with other one, then what will be the effect on the analysis? So I think here we just identified objects and synchronization points, and we just try to calculate the cost in form of execution time. Yeah.
Okay, thank you.
Okay, I see no more raised hands. Then thank you again, Rizwan, for this presentation. And we quickly have to find out if Diogo or Leila is giving the next presentation and promoting them to panelists, please. Diogo says it will be him. Looking forward to that. I still don't see Diogo in the list of panelists, but I'm sure Sergio or Marius is working on this.
Well, I cannot do it. Marius, can you do it?
No, I just sent a message to the host.
Yes.
There, okay, there's Diogo.
Oh, there we go.
Diogo, you can just go ahead, share your screen, unmute your mic. Let's see if this works.
Okay, you should be seeing the slides.
Yes, I see something. The sound quality just now was not optimal, but we will see. Okay, but I think we can just start. I have a slight déjà vu. I see graph grammars in the title. Module integration using graph grammars, MIGRATE. Joint work by Diogo, Raphael, Cravo, and Leila Ribeiro. Diogo, please go ahead.
Okay, so I'm going to present today the article Module Integration Using Graph Grammars, or the acronym MIGRATE, which already gives away our main goal with this tool, that is to automatically uncover integration issues when updating software. And this article was derived from my master's dissertation, which was completed earlier this year at the Universidade Federal do Rio Grande do Sul in Brazil. under the supervision of Leila Ribeiro, who is also a co-author here. And in this article, we basically summarize the dissertation.
Diego, 1 second. I have to session share a little bit actively here. Your sound quality is really bad. It sounds to me like a little bit, it might be actually a CPU problem, because this doesn't sound like an internet problem. Can you quickly check your settings if there's anything funny going on your end? Still not good. Of course, it could go.
Let me try to rejoin.
Are you using a kind of wired microphone or Bluetooth? Fortunately, we have a little bit of time to figure out these issues. Right now, we are like more than 1.5 years into the pandemic and hybrid and digital teaching, but there are still surprises after each software update. What setting is going to change this time? So you have my full understanding. Okay, I think he's restarting Zoom. Let's see if we have to invite him back onto the panel. Otherwise, I'm not sure if it would be an option that Leila tries from her end. In the worst case, we could also quickly swap talks, if that would be acceptable, but I think we'll just wait for Diogo to come back one time. And if the audio quality is still not sufficient, then I would say we swap the talks. I do not see him yet back in the list. Mhm. Otherwise, I would almost say we give Diogo and Leila the chance to conduct a little sound check with Zoom in general, and we continue with the other talk.
I think that's good.
Yeah, okay. Sidney, is this a surprise for you, or are you ready?
Okay, it's good.
Please go ahead. So we are swapping talks, and we will now be seeing a visual specification of properties for robotic designs. Yes, we see your slides. We hear you well.
Let me put
This is also
in
important.
full screen.
And we even see it in full screen. Yes, that seems to be the
Okay.
biggest challenge these days. Please go ahead, Sidney.
Okay. I am one of the authors of this work about visual specification of properties for robot designs. And this work is a result, partial results of Waldeck Lindoso master degree in computer science. And it's still ongoing work. Okay, so the context of this work is the verification of the software that controls a robot. There are many domain-specific language to design the logic of a robot control. But in this work, we focus on RoboChat notation because this notation has some interesting features. It has a tool, robot tool, in the right-hand side of the screen, where you can author using a visual language based on UML state machines. You can describe the interface of the platform, the hardware interface, where the controller that defines the operations that the controller, the software can call. Also, the events that are linked to sensors in the hardware. So the notation separates hardware is part of the platform and the control logic is software. So it's visual, and also it has a well-defined semantics, CSP semantics, and this too. So you can use FDR model checker in background to analyze the properties of RoboChat designs for a robot. Okay, so this is the context of our research. And checking properties in RoboChat, the engineer here, he designs the model, the controller using RoboChat notation. The robot tool automatically outputs the CSP semantics. And if you want to verify classical properties like deadlock freedom, live lock freedom, determinism, you just press alpha button, and FDR refinement checker says if the property holds or not. But if you want to define application specific properties, you need to write it by hand using the notation of CSP, and you have to know the underlying semantics for RoboChat model. So so you have to know CSP to write a property. And also, if the property does not hold, he has to interpret to see the counterexample that is also in CSP. This is not the most interesting scenario because many of the users of RoboChat are not from computer science, some are engineers. So what we propose is a different situation where the engineer describes the system in RoboChat, and also the semantics automatically generated by RoboTool. And what we are proposing is a notation based on UML state diagrams here in green. To describe the properties, the behavior of the property you want to verify. And you can do this using Asta UML plugin and Asta UML. And what we did was to make to implement a plugin that translates this notation to CSP also, and you can use FDR to analyze if the property holds or not. Another thing we proposed is that the counterexample is parsed and translated into a diagram, the sequence diagram. So the engineer doesn't need to see CSP or know details of the semantics. Okay, he works with RoboChat the visual notation and the sequence diagram. So before showing the notation and how it's verified and talk about a little its semantics, we need to know a bit about RoboChat. So here is a very simple RoboChat model. It is only part of the model because you have also the definition of the platform operations and events. But here you have the name of the state machine as movement. You have some definitions of the state machine and you have the logic using state diagram notation. So in the definition, you have, for instance, declaration that this state machine calls operations for the movement I, that is a platform interface. So the operations of this interface are implemented by hardware. So the software only calls the operations. And also here it says that the state machine inputs a platform event obstacle. This event, it happens on the controller whenever there's some sensor that is attached to the hardware sends a signal, okay? It's a platform event from the platform. Also, we have here two constants, one constant LV that is the linear velocity for the robot to move, and AV, another constant, the angular velocity of the robot when we call the move operation. So we see here, very simple behavior just for presentation purpose. This robot is very simple. The logic is to walk in a straight line, and when it detects an obstacle, it turns, it goes a straight line. So the move is called with linear velocity, different from 0 and 0 for angular velocity. When obstacle is detected, it changes the states to turning, and entering the state, it moves with linear velocity 0 and angular velocity different from 0. So the robot changes the direction and continues walking until the next obstacle. Okay, so knowing something about RoboChat, we can talk about our language. The language is based on UML state active diagrams. It's a very expressive notation where you have elements to express conditionals, loops, concurrence, and also you can decompose a diagram in subdiagrams. So we based on this notation, what we did was to adapt some of the elements, some of the nodes of the diagram to represent events and operations for RoboChat models. This is necessary because when we generate the CSP, we need to differentiate what is an input event, what is an output event, because the CSP encoding is different for each event. And also we have an element here to say that the name of the component that will be checked. Operations, you have a notation for operations. Apart from that, we also have in that language we added some abstraction patterns. So we have a stereotype here that we put in the transitions in the edges of the diagram. And also we have some stereotypes for diagrams. Okay, so when we put it together, we have an expressive language that's not as expressive as CSP, but is very interesting to a big set of behaviors that it can present. So here is an example of a property in this language. This is a state active diagram. So here in the swim lane, you have to put the name of the component that will be verified. So here you have a behavior that will be refined by this component. This idea is this, when you say the name. So inside here, the swim lane, we have a very simple property that it says that it is a loop that it expects for an obstacle input event, and after this obstacle the property says it expected a call to the move operation with 0 and 2, the value for parameters. And before the obstacle, the behavior of the property is to accept any other CSP event, and any event that's different from the obstacle event. Okay, here is not CSP, but what says is if you have an alphabet of events of your RoboChat model here. Okay, you do this looking for your RoboChat. So here you have, for instance, obstacle is an event from here, move is an operation from here. So you don't need to look for the CSP semantics. This is the idea. You just need to look to the model of the controller. So this is a sample property in the language. Whenever intuitively, the intuition is that whenever an obstacle is detected, the robot turns with angular speed of 2. It's what these operations say. So we define the semantics for the elements of this notation. So each of the nodes of the diagram, they are translated to a CSP process. And so in blue, you have the process that represents the nodes, and the nodes are linked with edges that are events in our semantics, and they process synchronize in the edges. So if the output edge is of one node, the input edge of the other, they synchronize using parallel composition of CSP operator, and they are executed in the sequence. And these elements are defined in the diagram, and they are encoded in CSP as process. In our semantics, we also have additional elements like a token manager, that is a CSP process that controls the determination of the diagram. Okay, so the idea is that you build a diagram, and then you have an automatic translation to CSP following this structure. And this is a composition semantics, so you can use you can use a combination of any combination of elements there in the diagram. We have only some restrictions on some on the stereotypes that we have created, that they cannot be applied in any place, but they can be applied in some specific place. But it's a composition semantics. Okay, we define it for each element of the notation. Showing a bit more about this sample with the sample properties on the left hand side. If we look to the CSP semantics in the right hand side, this is a semantics that is a simplification of it abstracts the parallel composition that exists in the semantics generated by the tool. The CSP specification has a lot of parallel composition, and the behavior of this parallel composition is a process that is equivalent to this process here that I'm showing. So if we put and verify the semantics of this one matched with the semantics of the property of the CSP generated by the tool. Okay, so just to give an idea, process property captures the behavior of this property here. Its behavior is it behaves as the recurse process that is a process that offers. It is defined here. This process offers all events in the alphabet of the parameter A. And then it behaves as the process P. And what we use recurse with the first parameter is the alphabet of events of the controller, except, so recurse offers all events except the event that represents the obstacle input event. So this process offers any event except obstacle, and also offers a choice with the obstacle event followed by a call to the move operation with parameters 0 and 2. So the idea is that this is it must be it is more abstract than the machine. This is the machine must be a subset of this. So the machine cannot make behaviors that are not described on this abstract property. CSP has this characteristic. We use the same notation for properties and the notation to describe the system. So to validate this semantics, we visited properties in the literature, and we described these properties. These properties were described directly in CSP, and what we did was to describe the properties using the proposed notation to see if our notation was as expressive to capture the same behavior of CSP process created to describe properties. Okay, so we use FDR to check whether the semantics of of our property defined using a diagrammatic notation is equivalent to properties in the literature using FDR. So we did this to validate if we were expressing the same semantics of some CSP process expressed by hand for properties. In CSP, a property is a behavior that is refined by the model. For in our context, RoboChat, we have a process RoboChat for the system and a process properties that express the property semantics. Okay, and the system behavior, it's a subset of the property behavior. It must be a refinement. With inputs in the plugin, we call FDR in the background and verify this kind of refinement. RoboChat, the trace of the RoboChat refine the trace of property. And if there is some counterexample, what the plugin does is to yield a sequence diagram that shows until what is if the model has a different has a trace counterexample. So in this example here, the model calls move operation, the platform generates obstacle event, and then the model calls move 00, but this is not in the property. It did not hold because the property says it must be after an obstacle 0, 0, and 2, the values for the call. Okay. So we do now a very short video for the tool. Here is the Robo tool. We did not implement Robo tool. Okay, it already exists. Robo tool is used to author the RoboChat model. So inside Robo tool, you press a button to generate the CSP semantics for this example. So it generated CSP semantics, and we have to switch to Asta UML plugin. This tool we use to author the properties using the notation elements available in the tool, and our plugin is already integrated in the Asta UML. So you have what you have to do is to select the file that represents the semantics for the model you want to verify. And after you do that, you go in a menu of the Asta UML tool, and you I'm okay. So and you press a button to check. In this case, we call it FDR in the background. FDR say, oh, this property doesn't hold, and we have a counterexample, and the plugin generated a sequence diagram to show the counterexample here. So you say what is the problem of the model. After you say the problem of the model, we can switch to the model again, and the problem if this is with the constant value that is 0, it must be 2 in order the property to hold. So I will accelerate here. If we change the model, we save the model, we generate the semantics for the model. We go again, we switch for the tool, and we check again if this property this time holds, and this time, okay, the property holds. So this is a short demonstration of the tool. Oh, sorry. Okay, we talking about existence work. This is the first work that we propose a diagrammatic language for RoboChat. Okay, the two first works are in the context of Robo2. So the first one defined a language where you can define some refinements and the check of classical properties of CSP. So in this first work, you need to know CSP to define the properties. The second work, it's very interesting for us because it modeled a lot of robotic properties by hand, and we tried using our notation to express using our language, and it was useful for our validation. And the third work, it's an example because there are other works that use some kind of diagrammatic language to specify robots. But on this third work and other works in the literature is outside the context of RoboChat. So the diagrammatic language is translated to temporal logics. It's different from our context that we work with CSP and refinement. Okay, just to conclude, we proposed this approach to hide the formal methods during the verification process. And it uses a diagrammatic language that we adapted from UML state sequence active diagram. We mechanized the translation, the verification, and the counterexample construction using a plugin that also hides the counterexample generated by the tool. As future work, we plan for more case studies. Also, we have to analyze soundness of semantics and several things on the approach. And also we plan to express properties with time constraint because RoboChat allows you to work with time, but by this time we only work with untimed models. That's it.
Thank you very much, Sidney. Do we have any questions? I'll give everyone a chance to type. I wasn't following 100% because I was emailing with Diogo. Is this just abstract work, or do you have like some real robot or even some industry collaboration or a concrete device that this is for?
The RoboStat project uses RoboChat and other notations with real projects and industrial patterns. So the notation is used in real robots. But during the development of this research, we are focused only on the validating the model properties. So what we did was to use already existent models that are in the website of the RoboStat project. We get the models and we get the properties, and we try to express them in the language and to see if and to validate if the semantics is the same using our language, and what we did.
Mm-hmm. Okay, thank you. Let me see if we have anything in the chat or in the Q&A. It does not seem so. And I also see that Diogo is back. So with that, we can return to our original, at least time schedule, if not the order. Thank you again, Sidney. Thank you for being available on such short notice. And Diogo is now in the list of
Hello.
panelists, and it sounds much better.
Okay, good.
Yes. This is such a big difference. Sorry for the trouble. Sorry for booting you from the session in that sense. But,
Yeah, I'm sorry.
no, it's like I said, it always happens. There's always a surprise if IT is involved. So without further delay, Diogo, please start from the beginning on your work on module integration using graph grammars.
Good. Thank you. And sorry for the trouble. Can you see my slides? Is it working?
Yes, everything's perfect.
Okay, good. So now I'm going to start, and I'm going to present today the article module integration using graph grammars, or the acronym MIGRATE, which already gives away our main goal with this tool. That is to uncover integration issues when updating software modules. And this article came from my master's dissertation that I completed earlier this year at the Universidade Federal do Rio Grande do Sul in Brazil, under the supervision of Leila Ribeiro, who is co-author here. And in this article, we basically summarized the dissertation. So the motivation, software is built on top of more software. We build our applications reusing existing modules that were written before by us or by others. And just as we reuse software as we develop, so do our peers, the dependencies upon which we're building. And if we take, for example, the JavaScript ecosystem with the Node Package Manager as its main repository, it contains over 1 million packages, and they're all linked to one another, giving rise to a really huge graph of module dependencies. And this happens to services too. And I would say it is even magnified by trends such as microservices, which in essence aims to minimize decoupling and avoid monolithic services, but at the same time can lead to such huge module dependency graphs. As providers of modules, the more dependencies our modules have, the more we need to watch out and keep our modules compatible with each change that we introduce. But at the other end, as consumers of modules, each time we update our dependencies, and we may do so for various reasons, from new features to security updates, each time we update our dependencies, we need to watch out for integration bugs. And I'll give an example. This is a JavaScript example, although it lacks code. It really is just this drawing. But we can tell it's a JavaScript example because it is using the Axios module, which is a very popular HTTP client for JavaScript, and it is available in the Node Package Manager. And a bug I'll briefly describe here is a real bug that I've come across recently while developing with this library. So I had a client, let's call it C, which used the Axios library to upload a file to a backend service. Let's call this service B. Now, Axios doesn't carry out the upload on its own. Instead, it uses another library called follow request, represented by FR here. So in summary, my client calls the Axios upload routine, while Axios calls the follow request upload routine, which performs the actual upload. And to my knowledge, in fact, there can be many other layers there of which I'm not aware, right? And when my client calls Axios, it passes a maximum content length value as one of its arguments, which Axios relays to the follow request library as maximum body length. And what happened is after I updated Axios, Axios changed the way it handled the maximum content length header, and it stopped relaying it to the follow request library, causing my maximum value to be disregarded. But more importantly, after this change, uploads started having a limit of 10 megabytes. And it took me days until I finally realized the reason why. And at that point, I really wished there was a tool that could point out my mistake before, if that were possible. And there are all kinds of things we can do to prevent those situations. For the case of services, we can try and relax APIs, making APIs that accept parameters that they don't need. And we can avoid to throw errors as much as we can. This is a pattern known as the tolerant reader, and it's described in Martin Fowler's website. And as I was reading papers, doing research for this work, I learned that Java actually contains a specification of compatibility in its very specification. But in general, even the type system of a language already helps us to catch some of those issues. Versioning is also great. And in the example I just showed you, that change was signaled by the developers of Axios as a breaking change. It's just that I wasn't aware of that change. Tests are also great to show regressions, but they're very difficult to implement when we want to test integration of many moving pieces. And creating new APIs and deprecating older ones is yet another tool that we can use to avoid those issues. But despite all of those things, we still have integration issues. And here comes MIGRATE. So with MIGRATE, we have a quite ambitious goal, let's say, of finding such errors in a fully automated way. And we want to use graph grammars for this, mainly because this is our domain of expertise. And in order to achieve this goal, we're introducing a new formalism that we call module network that describes how modules integrate to one another. And there is already a prototype for MIGRATE written in TypeScript and publicly available on GitHub in this website here. But I have to say, it can only handle very small examples, unfortunately, and that is for reasons we're about to see. This prototype integrates to two existing graph grammar engines, the attributed graph grammar system, AGG, and Verigraph. So AGG, like Leila said in her presentation earlier today, is developed by the Technical University of Berlin, while Verigraph is developed at the Universidade Federal of Rio Grande do Sul, and we use both of them because they have complementary feature sets. So this is MIGRATE on a diagram. Here on the left-hand side, we have 4 different artifacts, which are depicted in gray boxes, and on the right-hand side, we have 3 processes, which are depicted in the white boxes. And we're going to go into each of those boxes now. So software artifacts, they can be anything like source code or even service API specifications or execution traces. And the goal of the extraction is to take those, the extraction procedure is to take those software artifacts and produce a module net. Unfortunately, the extraction procedure isn't ready yet. It's still under development. But I'll just give you a brief insight. This didn't make it to the article because it really isn't ready yet. But I've tried to implement it for JavaScript using real JavaScript code. And what I found out is that this really is a very challenging problem because JavaScript has just so many versions and so many runtimes. And even the language, if I've tried to use a very popular parser for JavaScript, which is Babel, and I found that really there are tens, of abstract syntax tree nodes that combine in very different ways, and it's really difficult to parse, real production code. And also other challenges we have is to compute scope and to try to find the flow of information, which is really important for MIGRATE. It's essential for MIGRATE, and some language features make it even more difficult to compute those things. So really, this is just to say that the extraction procedure isn't ready yet, but it's a must for MIGRATE if you want to do this in a fully automated way. So the next step is the module net. So the module net is a formalism that describes how software integrates to one another, and it's composed of modules, operations, resources, and attributes. I'll show this in a bit. And it's just a syntax. It doesn't have semantics. The semantics of a module net is defined by the translation procedure. But more importantly is why are we introducing a new framework, a new formalism, sorry. And that's because it allows users to see the integration problem without knowledge of graph grammars. Now, graph grammars, they are very intuitive, but in our case, MIGRATE needs those grammars to be created in a very specific way. And with module nets, we can abstract that problem away. And also other reasons to create this module net formalism is that it allowed us to improve the verification procedure while I was developing it without having to rewrite our toy problems. And more importantly, we still don't have an extraction procedure, but we already have a prototype, and that's because of module nets. So here's an example module net. We have here on the left-hand side a graph where the nodes are, we call them modules, and the edges are operations. So in this case, the find article operation goes from the module website to the module research net, and the find document operation goes from the module research net to the module inventory service. And on the right-hand side, we break down each of those modules into resources and attributes. So the module website is composed of the resource search, and this resource is composed of the attributes DOI, title, and region. And under each of the resources and the attributes, we have generate, which is either true or false, and it means that this the value of this attribute or even this resource, it is generated by something external to the module net. And the require similarly is also true or false. It means that the value of this attribute or resource is needed to perform some operation which is not specified in the module net. Similarly, the research net module is composed of the article resource and the ID and history attributes, and the inventory service module is composed of the document resource and the location attribute. And down here we have the operations. So the find article operation, it goes from the search resource of the website module to the article resource of the research net module, such that the value of the DOI attribute is carried over to the value of the ID attribute, and the value of the region attribute is carried over to the value of the history attribute. And lastly here, the find document operation, it goes from the article resource of the research net module to the document resource of the inventory service module, such that the ID of the article is carried over to the location of the document. So this is a module net, a very simple one, just as an example. And the module net serves as input to the translation procedure. And this procedure is going to produce a graph grammar that we'll call the verification grammar. But the translation itself is also carried by another graph grammar, which we call the translation grammar. And this grammar, we've shown, we've proven that it has a very specific property, which is it has functional behavior. What it means is that if we provide it the same input, it's always going to give us the same output. So it's deterministic. And in order to have that kind of behavior in a graph grammar, we had to split its rules into 4 layers. So the first layer is the token generation layer. The second layer of rules performs the actual translation, and then the third and the fourth layers, they're just cleaning up some structures that are left behind by the previous layers. So here we have an example as a starting graph. This we can see here that we have modules and resources. This is a module net that has been encoded as a graph. And if we apply the first layer of rules to this module net, then we can see we obtain a bunch of tokens. And if we apply the second layer of rules, which is the one that performs the translation, it consumes all of those tokens, and it produces a bunch of graph grammar concepts here, as we can see the white background nodes. Yeah. So this is the translation. And as I said, the translation defines the semantics of the module net, because the translation produces a graph grammar, and graph grammars have known semantics. And as I said, it is also a deterministic process because it terminates and it is confluent. So this part we were able to prove. But this part here, that the translation produces a well-defined grammar, we only argue that this is true. We were not able to prove this yet. So the verification grammar, it contains, as I said, some very specific patterns. So its rules, they fit each rule fits one of 5 patterns. So it's either a require, which is a rule that has dependencies to rules that generate its attribute or resource. Require rules, they always require exactly one attribute or resource. There's the call and return rules, which are the call and return of operations. and they will always depend on rules that generate the attributes or resources that are needed for those operations. And then we have the generate and mock generate rules, which really are equal. The only difference between them is in the name, and they always generate exactly one attribute or resource. So the verification grammar is given as input to the verification procedure. And in this procedure, the first thing we do is we look at the verification grammar rules, and we try to find which are which roles each of its graph elements play. So we see whether each of the nodes is representing a module or a resource or an attribute. And we also perform the critical pair analysis on its roles using varigraph. And this is just a regular analysis that's already defined in the graph grammars theory. So when we do this critical pair analysis, we obtain a graph like this, where the nodes are rules, and the dotted blue edges are dependencies between rules, and the red solid edges, they are conflicts. So in this case here, we have a dependency from the rule that generates the search resource to the rule that generates the region attribute, and that is so because the region attribute is an attribute of the search resource. So I cannot have a region attribute without having a search resource. In the verification, we try to analyze this graph to find a few interesting information that we call hints. So one example of a hint here is a optional path. So in the optional path, we first try to find the roles which are of required type. In this case here, we only have one. And then we analyze this graph to find the roles which are not in any path that leads to a required role. So in this case here, this role here that generates the title attribute, it's not in a path leading to this required role down here. So in this case, we can conclude that the title attribute is optional. It really isn't needed. And there are also other kinds of analysis that we do on this graph. But the important thing is with the verification procedure, we generate a set of hints, and then we use those hints to generate warnings to the users that will be useful to them. So there are just a few kinds of warnings we have today. So we can tell whether an attribute is optional or a resource or a module or an operation, which means that those things, those concepts, that they are not contributing to reaching something that is required by the system. We also have strictly optional attributes, which means the same as an optional attribute. The only difference is that what we're calling a strictly optional attribute is something that is in the path to a required attribute, but it doesn't contribute to the value of that attribute. And we also have unreachable operations, which are which happens when an operation cannot find the information it needs in order to be carried out. Yeah. So the conclusion, there are really many limitations to migrate today. The first one is that module nets, they do not allow types of operations, and they also do not allow edges between resources of the same module. So today, the only kind of operations we have are reads. We do not have deletes or updates. And the solution to this in the future will be to try and define module nets as type graphs. That I think it's the easier part. The more difficult part is extending the translation to support those kinds of typed graphs. But this will also enable other more interesting kinds of warnings. Another problem is that the translation is difficult even for tiny module nets, because the host graph grows during the translation, as I've shown earlier. And this makes the problem of applying the translation rules harder and harder as the translation is carried out. And in order to solve this, we could try to split module nets before translating to try and control the size of the host graph. We could also improve the translation to avoid duplicated structures. We have our last layer today is only removing duplicated structures, so it would be better if we didn't create those structures in the first place. Also, prioritizing application of rules that remove elements helps reduce the size of the host graph. Also, another thing is that we already know that our translation grammar is confluent, so there is no reason why we would want to randomize matches. We'll always apply the first one. That would help us to save some time as well. Also, the verification procedure requires the critical pair analysis, which is very costly. But there are kinds of critical pairs which are much more restricted and therefore faster to compute, such as initial or essential critical pairs. And also we could think of creating just the critical pairs which are needed to our verification procedure, and that would also help us bring down the cost of the verification procedure. And finally, future work will be to extend module nets to support better warnings, as I said, improve the translation procedure, avoiding duplicates. We'll have to study critical pair analysis to simplify the critical pair process. And with all of that, we'll support bigger module nets. So today we only support very tiny examples. And of course, if we want this to be fully automated, we'll need an extraction procedure. And with that, thank you. And really, I would just like to say that a couple more remarks. This is the first time I've ever submitted an article to the conference, so also the first time I'm presenting. And I was very surprised that this article was accepted, because really it's just more than an example. It's barely a prototype. But I'm also very honored to have the opportunity to present this work here. So I thank you to everyone, to the organizers and the audience. And as a final remark, I would also like to say that this being the first time I'm presenting, and also because MIGRATE is just taking its first baby steps, I would like to say that any feedback is really very much appreciated. And once more, thank you.
Thank you very much, Diogo. So, who has some feedback or questions for him? Should still have ample graph grammar enthusiasts here from the tutorial earlier today. Diogo, it seems you have a pretty good understanding where the blow up for larger inputs is coming from, that you have trouble with larger models. I don't have the paper open by chance, but did you manage to quantify this, basically the complexity that is there under the hood?
Yeah, I don't think I put this in the paper. There is a complexity analysis in the dissertation, but I don't think we've added this to the paper. But really, so during the translation, the real difficulty is in finding matches for the rules. That is a very difficult problem as the host graph grows. And in the verification, most of the analysis that we do over the critical pair analysis graph. They are just graph. They're just walking over the graph, so that's mostly linear or polynomial time. But the critical pair analysis itself, that's a very costly process. So that's yeah.
I have some colleagues that also work with graph grammars and have developed their own tool, and then there's also translation to mod to execute some things as a rewriting system, and it's not easy to keep all the moving parts, the rules under control to get the most efficient execution of whatever you're doing, it seems. Yes. Okay, let me check. Do we have anything in the chat? It seems rather quiet there. Nothing in the Q&A either. Technically, we have 3 minutes left in this session, so if anyone wants, now is the time. Otherwise, we can only thank Diogo again for this interesting talk, nice slides, and thank you for sorting out your audio issues and not giving up, but trying and coming back.
Yep, thank you.
Do the chairs want to tell us something about the upcoming break and Jeanette Wing's keynote?
We should point out that it should be at 1 o'clock and not at 2 o'clock. It's a bit earlier. So in an hour, we will have Jeanette Wing keynote.
Okay. So thank you very much to Volker for chairing, and to all the presenters. And I guess we will see you in an hour.
Yes. Goodbye.
See you later.